Welcome to today's session of water and wastewater treatment. This is 10th week session from NPTEL. I am Saptarshi Bose, a BMW research call from IIT Madras. As usual, we will try to solve few numerical as well as conceptual theoretical questions. So the first one is common data question. So the concentration of calcium ion, magnesium ion and sodium ion are given in terms of milliequivalent per liter, as well as the bicarbonate ion concentration and sulfate ion concentration are given in the same unit. So from this bar chart diagram, you can find out what is the concentration of common ions present in the sample of water. So at the end, you have to calculate what is the carbonate hardness for this above water sample. But be careful, this unit should be in mg per liter as COCO3, not in milliequivalent per liter. Just a minute. Yes, use your chat section to write the answer, or in call message section so that I can check whether it's correct or not. I'll give you 2 minutes to solve this. Okay, I will go for the solution. So the correct answer is 175. And from the bar chart, you can see what is the carbonate hardness. So the carbonate hardness is here, that is 3.5, right? This is the carbonate hardness. So it's up to 0 to 3.5. So the 3.5 milliequivalent per liter is my carbonate hardness. So first convert it into equivalence per liter. What I have to do, I have to multiply with 10 to the power minus 3. So I'll get in equivalence per liter unit. Then you know what is the equivalent weight of calcium carbonate, that is 50, right? This 100 divided by the charge. Charge is for C2 plus and calcium CO3 2 minus. So if you divide this molecular weight with the charge, I'm getting this 50, right? This is gram per equivalence, and this was in equivalence. This was in gram per equivalence per liter. Equivalence is getting cancelled. I am getting as 0.175 gram per liter as CaCO3 or 175 mg per liter as CaCO3. So the next question is, what is the non-carbonate hardness for the above water sample in the same unit mg per liter as CaCO3? So the correct answer is 75. Non-carbonate hardness equals to, what is it? This total, this total hardness minus the carbonate hardness, right? So the total hardness equals to this one. From the chart, you can find what is the total hardness. Total is 5, right? After this calcium and magnesium, this is the multivalent ions present in the water. So this is my total hardness, is 5 milliequivalent. So I'm first calculating my total hardness, that is 5 milliequivalent per liter multiplied by 10 to the power minus 3 to convert it into equivalence. And same thing for calcium carbonate. This is 50 gram per equivalence, right? 50 gram per equivalence. This equivalence getting cancelled. I'm getting as 25 mg per liter as CO3. So the non-carbonate hardness equals total hardness minus the carbonate hardness. We already calculated the non-carbonate hardness, that is 175. If you might subtract that from 250, you will get 75 mg per liter as CaCO3. The next question is the water sample is, is the water sample admissible for hardness as per the Indian standard IES 10,500, 2012? You have to say depending upon the result, whether it's a true or false. This water sample is admissible for the hardness. Please write your answer in the chat section so that I can check, or in call message section. Okay, the correct answer is true. That is A, because the as per the permissible limit for hardness according to 10,500 IS code 2012, that is 600 mg per liter, and here the total hardness is around 250 mg per liter. So this is permissible. True. The next one is the wastewater treatment plant located in a city treats sewage water coming from various households. The pH of the influent water is 5, right? And after treating the wastewater, the effluent now has double the hydroxyl ions, so concentration. So the effluent water is having higher or the double hydroxyl ion concentration than the influent wastewater coming into the plant. So calculate the pH of the effluent. So that's your question. You have to calculate the pH of the effluent water, which is having double the hydroxyl ion concentration with respect to the influent wastewater. So I'll wait for 1 more minute, then I'll go for the solution. Please try to calculate by yourself. I have already done this kind of questions earlier in the earlier session. So the correct answer is 5.3. This is the pH of the effluent water. So the pH of the effluent was given as 5, right? So we know pH plus pOH will be 14. This is known to everyone. So pH plus pOH is getting me that the value of 14. So pOH will be 14 minus 5. Simple, that will be 9. So pOH we can write in this form also, minus log of OH concentration, that is equals to 9, right? So this is the negative logarithm of OH concentration. So the OH concentration is 10 to the power minus 9 mole per liter, right? So this was 10 base log. So I am getting 10 to the power minus 9 moles per liter, right? So the hydroxyl ions in the effluent will be this 2 times, that is double the concentration, 2 times 10 to the power minus 9 moles per liter. This is the effluent hydroxyl ion concentration. So pOH we can convert it, minus logarithm of 2 into 10 to the power minus 9. So the pOH I am getting after calculation, I am getting this as, just calculate in your calculator, you will get as 8.69897. So pH plus pOH equals to 14. Again, I am writing this equation. So pH will be 14 minus 8.86. Sorry, 8.69897, and it is nearly around 5.3. So the next question: permanent hardness of the water is also caused by the presence of what? Bicarbonates of calcium, magnesium, carbonate of calcium, magnesium, carbonate and bicarbonates of sodium, or the chlorides of calcium and magnesium. So the correct answer will be D. That is the chlorides of calcium and magnesium. So the permanent hardness of water is also caused by the presence of chlorides of calcium and magnesium. Why is because these are not the permanent hardness. Right? This is the non-permanent hardness we are getting this one, these things. and not from this. So avoid this one. See, why is the recarbonation done after lime soda processes? Is it for the removal of excess soda from water, removal of non-carbonate hardness, recovery of lime to lower the pH and increase alkalinity? Anyone wants to answer? A very easy question. So the correct answer is D. Okay, George, thank you for your answer. D, yeah, you are correct. So to lower the pH, we need to lower the pH because pH is high in case of lime soda process. You need to increase the pH first around 9, then around 11. So first around 9 to get the precipitation of calcium carbonate, then maybe 11 around 11 for the further process to precipitate the magnesium hydroxide. So that water we cannot consume. It's a very high pH water, so we need to lower down the pH using this recarbonation, using the carbon dioxide gas, and this will eventually increase the alkalinity, right? This will produce this carbonate or bicarbonate ions. So the next one, which of the following statement regarding lime soda process is correct? Lime removes carbonate hardness while soda removes non-carbonate hardness, or only carbonate hardness is removed, only non-carbonate hardness is removed. This one also very easy question. So the correct answer is A, that lime removes the carbonate hardness and soda will remove the non-carbonate hardness. Then the next question, select the correct statements. Single stage lime treatment is used for water that do not require the removal of calcium hardness, or the single stage lime treatment usually softens water to a final hardness of 70 to 100 mg per liter COCO3. The two-stage lime treatment is used for the removal of calcium and magnesium hydride. In split flow treatment, we can obtain desired effluent water hardness by the bypassing the flow. So the correct answer will be B, C, and D. Here you can see that single stage line treatment is used for the water that do not require calcium hardness. No, we go for the calcium hardness removal in case of single stage line treatment. So this is absolutely wrong. Then single stage line treatment usually sharpens the water to a hardness limit of 70 to 100 mg per liter of CaCO2. That's right. Two-stage lime treatment is used for the removal of calcium and magnesium hardness. If I have two different hardness like calcium and magnesium, then we can remove that using the two-stage lime treatment. And in case of this in split flow treatment, we can often dehydrate effluent water hardness by bypassing the flow. So in case of split treatment, what we do, we bypass certain water. This water is coming, we bypass this amount of water and we add here the excess lime. So this excess lime will eventually reduce the calcium carbonate hardness here caused by the calcium, and depending upon the magnesium hardness we can optimize how much water we should bypass and how much water should go from this directly. So the C and D is correct. The next question is, why is HCl and H2SO4 not used to decrease the pH after addition of lime? So we usually don't try to use HCl or H2SO4. Instead, we use carbon dioxide, right? So what is the reason behind that? Okay, so the correct answer is B, that is chloride and sulfate will result in unnecessary increase of total dissolve of solids, while it will not increase the alkalinity. But in case of if we are using the recarbonation using carbon dioxide gas, this will increase the alkalinity in the form of carbonate or bicarbonate. So this is one advantage I am getting. No, this is wrong because HCl and H2SO will provide enough H plus ions to lower the pH, as well as that fluoride and sulfate will again increase the carbonate hardness. No, we cannot say this is wrong because it will go for this non-carbonate hardness, right? And HCl will increase the consumption of lime. No, this is also wrong. It will not increase the consumption of lime. So the next question is hardness of the water is usually due to the presence of what? Among these four options, you need to choose. Okay, Georgia, I got your answer. Thank you. You are saying the option C, right? Fine. Yes, the correct answer is option C, that is magnesium and calcium. Depending upon these various options like the potassium, calcium, or the chlorine, potassium, and the calcium and chlorine. This is my correct answer. Magnesium and calcium. So select the incorrect statement from the following options. Permanent hardness is due to the dissolved chlorides and sulfates of the calcium, magnesium, or this permanent hardness can be removed by boiling of water. Permanent hardness is also known as non-alkaline hardness. The difference between the total hardness and the alkaline hardness gives the non-alkaline hardness. Okay, George, you are saying there is a B option, right? Yes, you are correct. That the B is the correct option. Permanent hardness cannot be removed by boiling of the water, and other options are correct. This is the incorrect one. That's why I'm saying this one is the correct one. Right? So the permanent hardness is also known non-alkaline hardness, and I already discussed in the previous numerical question. The total hardness equals to carbonate hardness and non-carbonate hardness, and it can be said in a different way as alkaline hardness and non-alkaline hardness. So, and also this one, the permanent hardness is due to the dissolved chloride and sulfates of calcium, magnesium. This is true. So only the false one is the option B. Next one, alkalinity of water can be defined correctly as what? What do you mean by alkalinity of water? Okay, so the alkalinity is it is measured the ability of water to neutralize H plus ions. So the option B is the correct one. Not it is related to the neutralization of carbonates, it's not related to the neutralization of hydroxide. So how much H plus ions can be neutralized, that will determine what is the alkalinity of the water. So boiler feed water should also be hard in nature, true or false? Yeah, George, right. This is absolutely false because it will cause the precipitation of calcium carbonate or magnesium hydroxide, and it will spoil the boiler, right? So that's why it's totally false. So HCl and H2SO4. Oh, okay. This one is already done. So thank you joining for today's session. I hope all of you have enjoyed and learned many things. So we'll meet in the next session on next Tuesday. Thank you for joining.